Alright, this video is to review for the honors chemistry test in covalent bonding chapter 9. So after basically I'm going to go over all the key things you need to do and be able to do or know for chapter 9, the test. One assumption is I assume that you can draw a Lewis structure, because I have another video you can look for on Shark Chem to how to draw Lewis structures. But my assumption is at this point in the chapter you know how to draw a Lewis structure. Key things you need to know. Well, first and foremost, you need to know that a covalent bond, chemical bond first of all, holds two or more atoms together. That's just a general description of a bond. But a covalent bond is all about sharing of electrons. So on the test, one of the things you want to be aware of is when we start talking about covalent, we're talking about sharing electrons. Because we learned about ionic bonds in the last chapter, and that was the transfer of electrons. So that's a key difference. So when you're looking at a covalent bond, you're talking about sharing, not transferring, because that's going to be ionic bond. We didn't really deal with metallic bonding, so you can pretty much ignore that. That's just on the slide. A couple definitions you need to know for a covalent bonding chapter. You need to know that electronegativity is how strongly an atom attracts electrons in a bond, because that's going to determine, one of the things you guys have been doing is learning whether or not a bond is polar or not. That's going to be determined by the electronegativity. That's the value you get on the chart. So you definitely need to know the definition for electronegativity. When we talk about what a polar bond is, it's basically the atoms have different electronegativities. That's when you do the subtraction thing with the bond energies, or not the bond energies, but the electronegativity values. You subtract those, and then what happens is you get a polar bond. So that's when we'll talk about that, and I'll do some examples as well. Covalent bonds, we already talked about, are described as between two nonmetals, so that's key. So if you're looking for covalent bonding on the test, it's got to be two nonmetals from the periodic table. That's what covalent is. And they're obviously sharing electrons. And then we can break it down, the bonds, even further using electronegativity. So before we even start, you guys have been drawing Lewis structures. So when you go and draw Lewis structures, a single bond is represented by a single line. Remember, a single bond is really two electrons, basically, when we'd have a line. A double bond is two double lines, basically represents, it's represented by basically sharing four electrons. And then finally a triple bond is going to really be, when you draw the Lewis dot structure, you're sharing a total of, whoa, hold on a second, I just drew that messed up. A triple bond is going to be where you're sharing 6 total electrons in a bond. Alright, how many electrons are shared in a double covalent bond? Here's an example. This was on your optional review paper. So if you talk about a double covalent bond looking like that, really what's going to happen is a double covalent bond is going to be that. The correct answer is 4. If I asked you about a triple, it would be 6. Single bond would be 2. Next one, which pair of elements is most likely to form a covalent compound? So if it's saying covalent, it's asking you for two nonmetals. That's basically what the test is asking you, or the question's asking you on this little practice test. It's asking you which one is two nonmetals. Well, if you look at the periodic table, sodium and chlorine, nope, that's a metal and a nonmetal, because remember, here's the haunted staircase that separates metals and nonmetals. So it's got to basically be, when you're talking about a covalent compound, it has to be sharing two nonmetals, and this is the nonmetal section of the periodic table. So that's not it. So if you look here, barium's a metal, so that's not going to be correct. Go back to a regular pen. So barium is a metal, sodium's a metal. We look at nitrogen and oxygen. If you go over here, nitrogen and oxygen are both nonmetals, so that makes that a covalent compound. That's an easy way to find a covalent compound. It means that they're all nonmetals, and then you have sodium and barium, which are both metals, so that doesn't make sense. A covalent bond, the definition, this is off the practice test you guys took, is sharing of electrons. So covalent and sharing they're synonymous with each other, so you have to be aware of that. Anytime we mention ions, it's going to be an ionic compound. Transfer of electrons is an ionic compound as well. So that's key for that. Which of the following is most likely to form a covalent compound? Same kind of question again. It's asking a covalent compound. So really what it's asking for is two nonmetals. Well, if you look right there, K is a metal. If I look here, Ca is a metal. Aluminum's a metal. Calcium's a metal, because when you take the test, you have a periodic table. So SF4 would have to be a covalent compound. So that's what you're looking for. Key things you need to know. Definition of covalent is sharing. And then basically two nonmetals are going to make a covalent compound. how do you classify a bond? If you remember in class, you got an electronegativity table for all the different elements. And all you're going to do is take two elements and you're going to subtract the higher value from the lower value in whatever bond you're talking about. So if you look right here, the bond difference they went over in class is, the ionic bond difference is 2.0 or greater. Anything when you subtract the two values, if it's 2.0 or greater, it's considered to be an ionic bond. If you get an answer when you subtract the two between 199 and 0.41, you're going to have polar covalent is basically what you're going to end up with. And if the difference is 0.40 to 0, then you're going to have a nonpolar bond. So when you look at it, it would look like this. And this is key because these occur on, you see these all as answer choices and stuff. Remember, you have to know the 7 diatomic molecules. An easy way to remember that is the magic 7. Nitrogen has the atomic number, starts with the atomic number 7. I always remember that. And I made that wrong. Hold on. Nitrogen starts with the atomic number 7. See how 6 of the diatomic molecules are in the shape of a 7 right there? So there's that, and you just have to remember hydrogen as well. So those are the diatomic molecules. When they're diatomic, they have the exact same electronegativities. Like hydrogen is 2.1 minus 2.1, 0. These are always going to be nonpolar molecules, always. So if they're looking for polar molecules or nonpolar bonds, or these are not polar molecules. These are all nonpolar. So they're all nonpolar. And all the bonds in these are going to be nonpolar as well. So it helps to know your diatomic molecules. It makes figuring out answers a heck of a lot easier. So if I had to take, for example, lithium and fluoride and classify the bond, how would I do it? I would go back to my periodic table, clear this off. Lithium's right there at 0.1 or 1.0. Fluorine's 4.0. So what I do is I go back over here and I subtract 4.0 minus 1.0 and I get a value of 3.0. When I go back and look at the chart, I realize that bond is classified as ionic because the difference is greater than 2.0. If I go back over here, bromine and bromine, this is what I'm talking about, where it's a diatomic molecule, it's automatically going to be 0. If I go down to carbon and hydrogen, for example, so I go to carbon and hydrogen, I look on the periodic table, carbon is 2.5, hydrogen is 2.1. So when I go to set it up, I go 2.5 minus 2.1. The difference in the two bonds is 0.4. When I go back to the chart, I see that anywhere in the region, basically anything that's below 0.4, 0.41 and above 1.99, so 0.40 is going to automatically be nonpolar covalent, and that's how you classify the bonds. All right. Here's an example from your practice test. It said the boron BF3. So if you look at the molecule BF3, here's what it looks like when you draw it out. BF3. Remember, boron is an exception to the octet rule, so it only bonds on 3 sides. So you draw this right here. They're asking you to classify the bond, not the molecule. So they're asking you for BF. So they tell you F is 4.0 and B is 2.0. So when you subtract the two, you get 4.0 minus 2.0. The difference would be 2.0, which according to the scale, it would be ionic. Only based on the scale, really. Next thing they ask you to be able to do is do molecular geometry. Molecular geometry is pretty easy as long as you can draw the Lewis structure correctly. So when you go to figure out the species formula, because you're expected to know the species formula, the way it works is you count the number of atoms attached. That's called a terminal atom. So all you do is count the number of atoms that are directly connected to the central atom. However many you have becomes the subscript right there. And lone pairs, like shoes, pairs of electrons on the central atom only. So we're only keyed on the central atom, and that gets us what's called our species formula. Once we figure out our species formula, we can also figure out the geometry, which requires a little bit of memorization, but I'll show you basically what the keys are. So if we come over here, steps to find it, we count the number of valence electrons in the model. Actually, we'll skip this. We draw the Lewis structure. You start at the center atom or central atom, and you count the number of terminal atoms. That's the M subscript. Then you count the lone pairs, and you get AX, M, E, N, whatever it is. I'll show you here. Here's an example. So if we go here, we zoom in on carbon is my central atom, so it's going to be A. There are 1, 2 terminal atoms, so it's AX2. There are no lone pairs of electrons on the central atom. So the species formula for carbon dioxide is going to be AX2. Then, once you know the species formula, you can come over here to the chart that you're supposed to memorize. AX2, The shape of the molecule would be linear. Its bond angle, just in case you're wondering, you should have taken it in your notes, is 180 degrees. Let's go back and do another one. I look at this one right here. Central atom again. AX2. No dots, no pairs of dots on the central atom, so I know the shape of this is going to be linear as well. I go here. My central atom, A, 1, 2, 3 terminal atoms, it's AX3. When I go to my chart, I look, AX3 means it's going to be a triangular planar molecule. So it's triangular planar molecule for that one. Let's do another one. We go over here. My central atom is N. So I go A, X, how many atoms are directly attached? 1, 2, 3. So it's AX3, E. Why? Because I have a lone, I have a lone pair of electrons on my central atom. That's the E. So that represents the E, AX3E. If I look right here, where'd you go? AX3E is going to be pyramidal. So it's going to be a pyramidal molecule. The bonding on that's going to be right around 107. I think it's 107.5. Check your notes, but it should be, actually, I have it here. Triangular pyramidal, the bond angle is going to be 107.5. So when we come back over here, another one. Now notice this molecule is only 2 elements. When it only has 2 elements, it's automatically going to be linear because it has to be a line. Look at this one right here. I zoom in on the central atom. I'm going to go AX4. No lone pairs of electrons, therefore it's just AX4. When I look at the chart, AX4 represents tetrahedron. Tetrahedron bond angle is going to be 109, should be 109.5. Where are you here, tetrahedron? 109.5 for a tetrahedron. So we'll write that on the chart, 109.5, and there you go. Planar is going to be 120. Bent with 1 lone pair of electrons is going to be 120. And then right around, nonlinear bent is around 105. 105 or 104.5, where is it here? Bent is right around 105, right there. 105, 104.5, right? 104.5 I think is what they gave you in the notes. So we'll say 104.5, I think that's what I saw. All right, so that's how you basically do species formula and geometry. It's pretty simple. Now, polarity. How do you do polarity of a molecule? Well, here you go. Which molecule has a Lewis structure that does not obey the octet rule? Remember, there are 4 exceptions to the octet rule. Be only bonds on 2 sides. Boron, the moron, only bonds on 3 sides, so it only gets 6. It's happy with 6. This is happy with 4. Those are incomplete octets. Expanded octets are going to be phosphorus, which can bond on 5 sides, and you have sulfur, which can bond all the way on 6. So this can take this can take the total of 12. This can take anywhere from pretty much a lot of times that it expands, it has basically 10 electrons. So when they ask you who does not obey the octet rule, you're pretty much looking for one of these 3 things. Now, if it does form an ion, that changes it. But if the molecule doesn't have a charge, then you're looking here, like for example, I have carbon. Carbon, that's not going to be carbon because carbon always bonds on 4 sides. It has 4 lines going to it, like if it's like here. Actually, that's not that's Cl. So if I look right here, it's C, Cl, 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 Cl. So really, the one that doesn't obey the octet rule is going to be phosphorus in that case. So phosphorus is the one you're looking for. Molecular geometry, NH2 minus. So if you basically draw this out, I'm guessing. And when you draw it out, you're going to end up with 2 lone pairs of electrons. The sucker is going to be bent. Why is this bent? Similar to a water molecule, you have 2 lone pairs of electrons, so it's actually going to be, when you draw it to shape, it kind of looks like this. You go and draw it to shape. You'll have this right here, like that. It could be even a little bit more bent, but the species form is going to be AX2E2 because of the lone pair of electrons. And the bonding on that would be 104.5. Okay? So draw the molecule, know the species formula that you have to have memorized. Now, how do you determine if a molecule is polar? We did bond. When it says bond, the word bond, you got to use the math. So when it says, you see bond in the problem? So if it says classify a bond as being polar or non-polar, it means use the chart. If it's asking you to determine whether a molecule is polar, that we get from looking at the Lewis structure. So the first thing is, If the molecule is diatomic, meaning it's only made of two atoms, if they're different atoms, they're automatically going to be polar. So like the one I showed you earlier with the ICl right here, they'll automatically have different electronegativities. This molecule is automatically polar. Why? Because it's different atoms. It's only made of two atoms, 1, 2, and they're different. So what's going to happen is you'll have an electronegativity difference that's going to make that molecule polar. An example of something that's going to be nonpolar we talked about is the diatomics. If I have Br2 and I draw a Lewis structure for Br2, looks like this, the electronegativity is going to be exactly the same. So the first thing is, it's going to be rare, but if they gave you two, on the practice test they gave you HCl, for example. HCl looks like this when you draw it. It's only made of two atoms, 1, 2. There's a difference in electronegativity, it's going to be polar. Second question, let's say it's not made of two atoms. Second question is, if the molecule has different terminal atoms around the outside, it's going to be polar, because it's not going to be symmetrical. It's not going to cancel out. What do I mean by that? Well, if you look right here, like here's BF3 right here. This represents BF3. When you look at BF3, I have the same terminal atoms on the outside, and then automatically I go to the third question, which is lone pairs of electrons, and there's no lone pairs of electrons on the central atom in this one, although it's not shown. Doesn't matter, the dots aren't on here, because it's a nonpolar molecule. Here's HCl. HCl is polar because there's two, and they're different elements. So if I go back over here, the last question is, if you have lone pairs of electrons on your central atom, you're automatically polar. If you say no to all three of these questions, it means you're nonpolar. So let's go back and look at based on the structures we were looking at earlier. We'll do polarity now. So I go over here. I look. First and foremost, is it made of two atoms only? Nope, it's three. Second question, lone pair of electrons on the central atom? No. Third question, terminal atoms are the same? Nope. They're the same. They're not different. So if they're not different terminal atoms, that means that molecule is nonpolar. I look here. It's not made of two. It's made of three. Second question, no dots. Third question, there's different terminal atoms. That's going to automatically make this molecule polar. You look here. Bam. This molecule. No lone pairs, but my terminal atoms are different. So when I go to classify these bonds, because what they want you to do is subtract. So you take carbon, you go 2.5 minus 2.1. The difference in this bond would be 0.4. But the difference in the carbon and oxygen bond, carbon is 2.5, oxygen is 3.5. The difference in that's going to be 1.0, and it's non-symmetrical. That's why that's going to be polar. We look at these. This molecule, instantly I know it's polar because of a lone pair of electrons, so that's polar. I go over here, two elements, they're different, that's going to be polar. I look right here. First question, no lone pairs. Second question, terminal atoms are the same. That is going to be a nonpolar molecule. That is how you tell after you draw the Lewis structure. Okay. Let's take a look here. If we look here, this is a nonpolar molecule. You have carbon, but you have 1, 2, 3, 4 same terminal atoms on the outside, means the molecule is going to be nonpolar. This is polar. They don't show it, but it has a lone pair of electrons when you draw NH3. The lone pair of electrons there is going to make that sucker polar. So right there and then with the lone pair of electrons, that makes it polar. You look here. You look at this molecule, CH3Cl. So I see CH3Cl. Automatically, I know that it's not going to be a symmetrical molecule. Plus the bond here, if I go and classify it, chlorine, I believe, is 3.0. I think. Let me go back and look. Actually, I think it might be 3.5. Chlorine is 3.0. Carbon is 2.5. So that's going to be considered a polar bond based on the subtracting it. So if you look just at that molecule right here, 3.0 minus 2.5, I'm going to get a 0.5 difference. These aren't going to cancel out. It's non-symmetrical. So therefore, that molecule is polar. So you can just by look at it. Which of the following is a non-polar molecule? Well, if I look, H and Cl, two atoms only, and they're different, that's going to be polar. Water, by now, you should almost know what water looks like from taking biology. Water is extremely polar. It has two lone pairs of electrons. NH3, you've probably drawn a bunch of times. It's a very common molecule. Even on like AP chemistry, it's used a lot. NH3 looks like that. Lone pair of electrons. CO2, that's what your CO2 molecule looks like when you draw it correctly. It has two double bonds. Double bond here, double bond there. No lone pairs of electrons. The terminal atoms are the same. That's what makes that sucker polar. If you look right here, they're talking about a CF4 molecule. So you go and draw, this is off the optional review. When you draw a CF4 molecule, this is what it looks like. Looks like this when I'm all said and done. Now, what are they asking me? First and foremost, when you read the question, they're asking you about the bonds in it, and they're asking you about the molecule. Well, overall, if you look at the molecule first, there's no lone pairs, and the terminal atoms are the same. So therefore, I know the molecule is nonpolar, which means I eliminate D as an answer choice, whoa, and I eliminate B as an answer choice. So then I have to determine the bonds. When I go to determine the bonds, I just look at the individual bonds. They're all the same, so I'm going to do CF. F is 4.0, C is 2.5, the electronegativity difference is 1.5. Therefore, if you look at the scale, that is a polar bond. Each of these are polar bonds. Why is the overall molecule nonpolar? If you look, it's because of this. The fact is, they're polar, but they cancel each other out. When the terminal atoms are different on the outside, or when the terminal atoms are the same on the outside, the forces will cancel each other out, and overall the molecule is nonpolar. So when you go to do it on a test, if they ask you, pay attention to whether they're asking you a bond, means do the math, and for each 2 atoms at a time, a molecule means you got to look at the whole thing, the whole enchilada. Hope this helps. If you have questions, you can email me. I'll try and answer them, do whatever I can. All right, you guys enjoy your Thanksgiving. Have a good break.